Now, any questions before we begin? Okay, so in the last example that we had this cart, what we can think of is, well, there's this object. We might not be looking inside. So in our cart example, this was just, there's a cart in it, and there's a guy standing throwing balls. But what an outside observer would see is we have this cart, and there are these balls, and assuming that the man is constantly throwing balls to the wall, we will have all these balls moving in this direction. So at the end, this cart will be moving in the forward direction. It will be gaining some velocity in the forward direction. This is basically how a rocket also works. So you are just using some chemical energy most of the time. And by burning some gases, you just heat them up. You obtain a gas at very high temperature and hence high pressure. So there's a hole, so-called the nozzle. And through the nozzle, you just let the gas go. So as the gas is moving backwards, just to conserve the momentum, you should be moving in the forward direction. So let's see how we can calculate how the velocity of this rocket will change as a function of time or as a function of its mass. Now, initially, let's say, this is the, well, let me draw a better graph. At a given time t, this is my rocket. Let's say it is moving with some velocity v, with some speed v in this direction. And let's assume that in the rest frame of the rocket, I mean, if you go back to the example of the cart, the guy is just throwing balls with some constant speed. Let's say that at the rest frame of the rocket, we are in this rest frame. The gas goes back with a velocity u. So, or you can say that you are sitting on the rocket. It might not be an inertial reference frame. I don't really care. But you just look back at the gas from the exhaust, and you will see that when they leave the exhaust, they will have the speed u. That is your observation as a guy sitting in the rocket. You just look at your exhaust, and you see that it's moving away from you with the speed u. Let's now go to the inertial observer. Now, the inertial observer, we just look at the rocket, and we see that it's moving at some velocity v. Let's say that at this time, the total mass is, let's just call it m of t. Because as it's burning fuel, the mass of my rocket will be reduced in time, because as an exhaust, I'm just throwing away some mass. So what is the momentum of my rocket? Let's say in the z direction. The initial momentum mass times the velocity or the speed. Since we are just looking at the component, is m times v. This is at time t. I just look at the rocket, I see that its mass, or I just call my friend to ask what the mass is. This is the mass, and I measure its speed. So at time t, this is the initial momentum of my rocket. Of course, it's in that direction. And then I just wait a very small amount of time at t plus dt. The rocket will be moving at speed v plus dv, let's say. It just speeded up a bit. Its mass is now m it's losing some mass. Let's say that it's m minus dm. dm is positive. That's how I define. M minus dm. And there is an amount of exhaust. Its mass is dm. And what's its speed? Y zero? Well, you see, the rocket is moving in that direction with a velocity v. The exhaust, I just emit the exhaust in this direction with velocity u prime. The velocity will be just v plus u. U is in this direction. I know that if I am moving in that direction with a velocity, with a speed v, if I throw the exhaust in that direction with the same speed, then it should be 0. Well, this makes sense in that case, because v is in this direction, u is in the opposite direction, so I just sum them up. Of course, the speed will be, this will be equal to v minus u in the z direction. You see this, the velocity is v minus u in the z direction, because v is in this direction, the velocity of the rocket is in this direction, the velocity of the exhaust in the rest frame of the rocket is in this direction, in the minus z direction. What is the final momentum? So the final momentum will be, what is the mass of the rocket, the remaining mass? M minus dm. What is its velocity in the z direction? What's the velocity in the z direction is v plus dv plus, what is the mass of the exhaust? Remember, my whole system is the rocket plus the exhaust. That should, the momentum of this whole system should be conserved. Initially, the rocket was moving with speed v, its mass was m, so the initial momentum was m times v. Now, some exhaust has left with a speed v minus u in the z direction, and my rocket has now speed v plus dv in the z direction, so this is the momentum of my rocket in the z direction. And then I have to add the momentum of my exhaust if I want to obtain the total momentum of my system. And this will be dm times v minus u. So this is the final momentum of my system. And remember, the initial momentum was just m times v. Now I'm just imagining that I have this whole rocket. It just divided into two. This is the rocket. This is the exhaust that we just throw away. This is the speed. This is the mass. The total mass of the system after I throw away this exhaust should be equal to the total momentum of the system before I throw away the exhaust. M times v should be equal to, okay, now I will just multiply these parentheses. M times v plus m times dv minus dm times v minus dm times dv plus dm times v minus u times dm. So I have this equality. These cancel. I have dm times v. These cancel. This is negligible. Remember, eventually I will be taking the time to go to 0. I'm just looking at one time, and I'm just looking at the same system at right the next time. So typically, let's say this dv will be of the order of 10 to the power minus 5, the initial velocity. dm will be 10 to the power minus 5 times the initial mass. So this product, dm times dv, will, all these terms will be of the order of 10 to the power minus 5, let's say, in suitable units. this will be 10 to power minus 10 in suitable units. So this is much, much negligible compared to the other ones. So these two terms should also cancel and give me 0. M times dV should be equal to U times dm. Now we can do one more thing. We can, for example, just divide it by the time it takes. Now we can do various things with this one. So what this tells me that, assuming that I look at my system for a very small amount, I measure the mass, the change in the mass, I measure the change in the velocity in a very, very small amount of time. Then the change in the speed of the system and the change in the mass of the system should be related by this. Now, if we divide both sides by dt, mass times the acceleration of the system, of course, remember, this is the mass at a given time times the acceleration of the system at that time is equal to u times dm by dt. Well, you can treat this as if, this part at least, you can treat it as if it's a kind of a force. It's not exactly like a force, because Newton's second law, it was written for constant masses. It was just a constant. It was not time dependent. But in our case, the rocket will have a time dependent mass. Nevertheless, if you just treat this combination as the force, you see that the force that the exhaust exerts on our rocket is proportional to its speed. The faster you throw away the exhaust, the faster you will go. The larger the acceleration will be. And dm by dt is the rate of change of burning fuel. If you burn the fuel faster, you will be gaining a larger acceleration. For example, one of the alternative rockets, most of the space ships that we have, they are using chemical reactions, chemical fuels. So you burn the chemicals. When they burn, they create a gas which is very hot. It expands. It goes out through the nozzle at some speed. Well, the maximum speed that we can reach is the speed of light. But no matter can reach the speed of light. One alternative scenario, if one day we can create antimatter, when you bring in matter with antimatter, how many of you watched the Demons and Angels and Demons, or Raised the movie? Okay, if one day we can produce antimatter in abundant quantities, we can just take antimatter, matter, put them together, they will annihilate, and when they annihilate, they will just create light. And light moves at the speed c, the speed of light. So that will be one of the we would be able to reach one of the limits over here. That is one possibility at least. Now let's go back here. This is one way of calculating it. Now another thing that we can obtain is what will be the final speed of my object. Well, this is how the speed changes as a function of time, but we can also calculate what can be the final speed. And to do that, let's go back to our initial relationship, mdv. Here we had the mdv is equal to u dm, or dv is equal to u times dm over m. If you burn this dm amount of fuel when the rocket has a mass m, this will be the change in velocity. If we add all these changes, initially, let's say the rocket has some velocity v0, and finally it has a velocity, it has a speed v. This is when I'm summing all the changes, this should be equal to, u is just a constant. This is the initial mass, the final mass, so this will give me v minus v0 is equal to u plus logarithm of the final mass divided by the initial mass, or v is equal to, no, not plus, v0 plus u times the logarithm of the final mass divided by the initial mass. Okay, so as usual, we will ask, does this relation make sense? Okay, this is one thing we derived. But does it make sense? Now, you should always ask, whenever you obtain a relationship, you should always ask yourself, does it make sense? For example, in the midterm, in the last question, some of you had made some computational mistake and obtained that the forces that you should exert should be 10 to the power minus 4 newtons. Well, 10 to the power, I'm exerting something like 1 newton to this one. Okay, so if imagine you are going in a car, you're in a car crash, if you want to hold something, you will definitely exert a force that is larger than 10 to the power minus 4 newton. So if you would have asked yourself whether your result makes sense or not, you should have guessed that your result is wrong, and you could have gone back, try to find a correction to this. Now we are asking the same thing. Does this make sense? It depends on E. Why? So?
When we could change this equation properly, we find an equation depends on E.
Okay, so?
I don't know, it's just interesting.
It depends on one also, but E is just something natural.
E is constant.
No, E, the natural logarithm is something natural. That's why it's called natural. It always appears. It's not a surprise. But let's look at one case. Suppose that the final mass is, let's say, half the initial mass. So do you remember the properties of the logarithms? So let's say the final mass is less than half the initial mass. You burn half of your total mass. In a real rocket, you burn more than half your mass. What remains of the rocket is a very small percentage of the initial mass. So the final mass is half the initial mass. So m final minus m over m initial is 1 over 2. Now, logarithm of 1 over 2, I will not ask you what its value is. Is it positive or negative? It is negative. So you see, this is a negative number. So the final velocity of our rocket is smaller than the initial velocity of the rocket. So what went wrong? No, it's just the speed. We defined it to be positive. So, we are always, up to here, I always treated the v and the u as speeds. And since they are in opposite directions, this is why I have this minus over here, because v and u are in opposite directions. Okay, there's a subtle point here when you are doing the integrals that you should keep in mind. You see, here we define something. Let's see, dm is larger than 0. You see, I also had this tendency of ignoring such things. It's obvious, right? dm is larger than 0. But let's come here. dm is not really the change in the mass, it's the reduction in the mass. You see, by making these small changes in dm, which is positive, you cannot go from m initial to m final, because dm is positive, remember. If you want to go from m initial to m final, the change in the mass is negative, not positive. So here, this dm is in fact the mass of the exhaust. Let's say dm, or change in the mass of the exhaust. let's just denote by small dm. Change in the mass of the rocket. Now we can do two things. Either we can convert everything, dm, to minus dm, because if I throw away some mass, the exhaust, the rocket, the mass of the rocket will be reduced. The change in the mass of the rocket will be negative if the change in the mass of the exhaust is positive. Either I can convert everything into dm. In that case, all of this thing will be correct, and here I would end up having a minus sign. Or if I want to stick to this dm, this large m is the change in the exhaust. So the change in the mass of the exhaust is the exhaust. Initially, it had 0 mass. Finally, it had m final minus m initial. Now, m initial minus m final. This is the mass of the exhaust. But of course, we still need to make some more changes, because if large m is the change in the mass of the exhaust, this large m, what we used was the mass of the rocket, the remaining rocket. So we have to also correct this one. Well, that will take a long time, so let's stick with the other one. This will, okay, let me, so v minus, so these limits over here. Now, this is the mass of the rocket. dv is equal to minus u d times mass of the rocket. So is this clear why we have that minus sign? Because initially we described dm to be a positive number. But a positive number cannot be the change in the mass of the rocket, because the rocket is losing mass. So that's why here at this point, we explicitly make the conversion to the change in the mass of the rocket. So the rest is the same. dv is equal to minus u, the mass of the rocket, divided by mr. Velocity goes from v0 up to the final velocity as the mass changes from the initial mass to the final mass. And we obtain v is equal to v0 minus u logarithm of m final over m initial, or v0 plus u times the logarithm of m initial over m final. Now it makes sense. Because if the final mass will be always less than the initial mass, so this logarithm is always a negative number, so the final velocity will be always larger than the initial velocity. Now this is a, let me also change over there, dmr. This is a subtle point that you have to keep in mind when you are making these integrations. It will cause confusions quite often. Now, except on this part, do you have any questions? I mean, what we have used is basically just the conservation of momentum. We identified the initial momentum, the final momentum. Well, of course, in this case, we had, I mean, when we are dealing with conservation laws, I said that most of the time we ignore what happens in between. We have the initial mass, initial quantity, the final quantity. It might be a very large amount of time in between. You just ignore what happens in between. You just have to equate the two masses. But the problem in this case was that the exhaust, the speed of the exhaust depends on the speed of the rocket. So as the speed of the rocket is constantly changing, different parts of the exhaust have different velocities, have different speeds. So to avoid that problem, what we did was we just looked at the momentum at two different times that are separated by a very small time interval. to determine how the velocity changes as a function of time. So what we did was, at one time, we have the mass, the velocity, so we can calculate the initial momentum. At the next moment, we have the velocity has changed a bit, the mass has changed a bit. The exhaust, there's a small exhaust which has its own velocity and mass. And we just equated the two momentums, and at the end of the day, this is what we obtained. Now, this is a relation that relates the change in the mass, a very small change in the mass of the rocket, to a very small change in the speed of the rocket. And if you want to calculate the total change, the only thing you have to do is you just have to sum all the changes. Now, by the way, there is one more point to note here. dm over dt is larger than 0. It is not the rate of change of the mass of the rocket. It is the rate of change of the mass of the exhaust, which is minus the rate of change of the mass of the rocket. Okay, question?
In the equations, there's something negligible.
Yes, this one. Well, you see, the exact equation that we have would be mdv is equal to udm plus dm times dv. This is the exact equation. But let's see what this equation means. Also, always keep in mind that eventually the t dt, the change in time that we make observation, this dt will be 0. For example, what we had done here was, one thing that we had done was divide by dt and take the limit as dt goes to 0 of both sides. Now let's see. The left-hand side just becomes the mass at the time t times the acceleration of my rocket at the time t is equal to u times the rate of change of the mass of the exhaust. Well, if dt goes to 0, both the change in the mass, the change in the velocity goes to 0, such that dm over dt is finite times limit as dt goes to 0 of dv. This limit is 0. So you see here, this is fine. This is a finite number. This just tells me how fast I'm burning the fuel. But this is 0. So this doesn't contribute. In this limit, this term is 0. It doesn't contribute. Of course, if I'm taking a finite value of dt, then what I write over here, mdv is equal to udm. If I keep dt to be a finite number, then this is approximate. But this result is exact, because this result I'm writing in the limit that the time interval I'm looking at is 0.
That's also a virgin. I think. Yeah, that's the limit is 0, but not exactly 0.
Exactly 0.
Exactly.
Well, that's what you prove in the calculus courses. It's exactly 0.
But is dt not 0?
If dt is not 0, of course, this is only approximately true. There will be an error bar. But if you can take dt to be small enough, the error bar introduced by ignoring this term will be much smaller than compared to the error bars in your measurement.
Conservation of momentum
Is exact. Conservation of momentum is exact. And conservation of momentum tells me that these two things, I have this equality. That is the conservation of momentum. No, I mean, in this equation, even dt need not be 0. This is what conservation of momentum tells me. This is what conservation of momentum tells me. This is exact. Now, of course, if I know how much I fuel per unit time, then I can calculate the acceleration I can calculate the instantaneous acceleration from that knowledge. And the instantaneous acceleration at the time t will be nothing but 1 over mt u dm over dt. This is also exact, because this is instantaneous acceleration. This is the instantaneous rate of burning fuel. This is again exact. If you don't take the limit dt goes to 0, this equality, the equality of this term to this term is approximate, but we always look at instantaneous properties. Most of the time we are interested in instantaneous properties. Also, the meaning of the term exact in physics and in mathematics, they are a bit different, in the sense that in mathematics what we say that something is nothing is exact in physics. Everything is up to an error bar. So if that error bar is small enough for us, that is exact. If the theoretical calculation and experimental measurements they agree with each other within error bars, then our results are correct. Other questions? Okay, let's do one more example. Now let's assume that we have this, again, along the line of the cart, remember, we had this wall. Let's assume that we have this mass. It can be a wall. And you throw objects of each one with mass m. They have velocity v, or let's call it u. And what they do is when they hit your mass, they just bounce back. And what you are actually doing is, let's see, you are sending number of hits per unit time. And let's just assume that you are sending them quite fast, not just one by one. And if you want to keep, well, of course, I mean, this one will be moving. If nothing else prevents it, the mass over here will start accelerating in this direction. It will start accelerating to conserve momentum. To prevent its acceleration, let's say you exert some force F to stop it from accelerating. What will be the average value of F? Now remember, the average force we usually define, if the momentum of an object is changing, the average force will be the change in the momentum divided by the time it takes for that change. This is how we had defined the change in the momentum. Now, of course, the momentum of my large mass is not changing, so the net force acting on this one should be 0. I am exerting one force, while these balls should be exerting some other force to balance the total force, so the total force should be 0. But for that to happen, the average force that I exert should be equal to the average force that the masses exert on my mass, on my box. But the average force that these masses exert on my mass is equal to the average force that my mass exerts on my box exerts on these balls. So to calculate the average force that I exert over here, I can just use this one. Now for each ball, what is the change in the momentum? One ball, the magnitude. What is the change in the magnitude of its momentum? Initially, it is m times u in that direction. Finally, it is m times u in this direction. So what's the change? It's just twice mu in that direction. So the magnitude is 2mu. Let's say in a time delta t, how many collisions are there? N times delta t. This is the number of collisions in delta t. So the change in momentum in delta t will be just number of collisions times the change in momentum in each one of the collisions. It's 2mu n delta t. Momentum change in delta t. This is the momentum change of the balls. Well, if this is the momentum change, divide by delta t, that will give you the average force. This is equal to 2m/u. So this will be the average force exerted on my box during this time. So what we did is we just looked at, first of all, we had to determine what we want to calculate. So you have to be clear on what you are aiming at. In this case, we wanted to calculate the change in the momentum of the balls in a time delta t, so that we can calculate the average force exerted on the balls. Remember, this is what we have actually calculated. We have calculated the average force exerted on the balls. But we know that the average force exerted on the balls by my box is nothing but the average force that the balls exert on my box, because of Newton's third law. The force that my box exerts on the balls is the same as the force that the balls exert on my box. So I calculated the average force on the balls. That gave me the average force on the box. Of course, they will be in opposite directions, but since I'm considering only the magnitudes, I don't care about the direction. So 2m and u. By the way, this will be a simple model. Why there's drag force to start with? A drag force. You see, it will be just a bit more complicated in the sense that your box will be just moving in a region where you have all these small balls that you call the molecules. So this is why you create a drag force. Or why the gases exert a pressure. Because a gas is nothing but you have an enclosure, the atoms are moving around, and they will eventually hit the wall. And when they hit the wall, they will exert an average force. Of course, there are a few other quantities that we have to specify, like how many collisions are there per minute, per unit time, but we will probably do it at the end of the semester. So this is basically the idea why there is pressure or why there is a drag force. Okay, any questions before you go? Yes, one question. Yes? No? The total average force acting on the box is 0. But the average force that the balls exert on the box is, again, has this magnitude. Okay, see you next Tuesday or Thursday.